Hey everyone, so welcome back. We're going to kind of continue off of where we left off after the Google Slides project. So you guys now have the fundamental vocabulary that we need in order to start geometry, but before we can really get into anything else, there's another set of rules essentially that you need to you understand. Geometry is built upon these ideas called postulates, and what postulates are essentially, or also referred to as axioms, is they're statements or rules that are accepted to be true and cannot be proven. Okay, so essentially they're the building blocks of everything that's going to happen. So now you have the definitions, right? And once you kind of learn the postulates, then you're able to really start working within geometry and exploring new ideas and kind of how everything relates and ties together. Because remember, geometry is a lot more concept based versus just simple x's and y's, threes and fours. Okay, so the first few postulates that we're going to talk about deal specifically with points, lines, and planes are three undefined terms. Okay. Again, if you need to review those, please go back to the Google slide and kind of review the ideas of what those are. Okay. What I'm going to do today is I'm going to demonstrate like what the first postulates on using this program called GeoGebra. And so we're going to go through each one and I'm going to show you kind of how it works or why it works in not only one, but not only two, but three dimensions. Okay, because some of these objects, you can put them on a sheet of paper. Others, it's harder to visualize. So I'm going to try to give you a little bit more visualization. Right. So the first postulate that we're talking about is through any 2 points, there is exactly one line. Okay, and kind of what that means. So in this example, we have points P and R, and I can draw exactly one line through points P and R. Does that mean that there's only one line that contains P and one line that contains R? Absolutely not. What it means, though, is there's only one line that contains both of them. And kind of just showing you what that looks like. Again, I'm going to be going back and forth with this. Okay, so here I have geometry or GeoGebra, which is basically just a canvas for me to draw on. So I'm going to put a point A here, and then I'm going to put a point B here. Okay, now what makes this different is I can try to draw different lines. I can try as hard as I can to draw a line that goes through A, and I can kind of hover it through B, right? But if I try to, again, even go B to A, if I try to draw any other line that kind of goes through A and B at the same time, it's always going to overlap and it's going to be the same line. And that's simply because when we define a line that contains both these points, so remember, a line is infinitely small. It has no thickness, but it does have direction, right? And it is made up of an infinite set of points, okay? And so in order for me to draw through these two, right, the only other way I might be able to do it is something where I kind of go, okay, well, here's A and here's B, right? That's maybe what you're thinking as far as trying to draw it. Well, that's clearly not a line. Remember, we defined a line as essentially not necessarily the shortest distance between 2 points, but the shortest distance between any 2 points lies along the line that's between them. And I know that kind of can get confusing, but that's essentially the best way to describe it, is essentially what is the shortest route that I can get through between A and B. And again, in different geometries, it looks a little bit different, but for Euclidean geometry, it's always going to be that line. Okay, so this semicircle here is definitely not going to be the shortest distance between those 2 points. So let me just undo here. And so this is our line that goes through AB. So, and again, in what that might look like, for instance, in the coordinate plane, is if I have this point, let's just go 0, 1. I'm sorry, yeah, 0, 1, and then this other point, 4, -1. There's only one line that's going to go through them, and you guys can write the equation of that line, and we've worked on writing the equation of that line. So I can go from A to B. The only line that's going to be is going to be a line that has a slope of, let's see, rise, so -2 over 1, 2, 3, 4. So essentially a slope of -1/2, right, with a y-intercept of 1. Okay, and again, you've seen instances like that before. Now, if I go to, I don't know why that's going like that. That looks weird. Okay, forgive that. That was a very awkward and weird thing that just popped up. So if we're going to go into three-dimensional, so I'll quickly explain this. This is GeoGebra's three-dimensional model, and it's basically a graph in using 3 dimensions. So Nothing. I can move this around here, and so I can get different looks and different perspectives at different things. Because remember, we're trying to solve geometry in the real world, and our real world has 3 dimensions. It has depth to it. So what does a line or a point even look like in 3 dimensions? Might look a little weird. Okay, so I'm going to put a point. Let's just put one in here, and I'm going to put a point just kind of. Let's see if I can do this 1 second. I'm going to put one just arbitrarily. See if I can put one like here. I say arbitrarily, but so essentially I've got 3 dimensions. Okay, and if I kind of look around, we can see that A and B are in. I can draw a plane between them, but essentially, or in some sort of sense, right? But they're both in separate planes here. Okay, I've got A, B in what we call the XY plane, and then B is just sitting over here on what we call the Z axis. Okay, and again, I can move it around. I can look, but then what does a line look like? Right. So is there more? If we're in 3 dimensions, are there more lines that I can draw? Well, let's try it out. So let's just try and draw a line that connects A and B. Well, if I spin this guy around, right, you're going to notice that there is only one line that is going to go through them. Okay, through both of them. No matter which way I spin it, no matter what it looks like, A and B, there's only one line that I can draw. Now, if I move A, for instance, that line's going to move. Okay, if I move B, same thing. So when we talk about kind of Euclidean geometry, and we talk about geometry in one plane, if A and B are both in the same plane, right, in fact, if I kind of hold it up like this looks very familiar to what you normally graph with. I have my x-axis, I have my y-axis, right, and here I have my normal line. But in 3 dimensions, sometimes that might look a little bit different depending on my perspective. Okay? And so that's the first postulate. Okay. Through any 3 non-collinear points, there's exactly one plane. Now, again, this is since planes are 3-dimensional figures essentially, or they exist within 3 dimensions. It's really hard to draw one in 2 dimensions because the entire surface in 2 dimensions would be considered one giant plane, and there's no more that I can really draw through it. So what I'm going to do is I'm going to look at it in 3 dimensions. So here I have 2 points that are collinear, but I'm going to put another third one that's anywhere else but on this line. So I'm going to use it in the same plane as A, so to speak. But as you can see, we have 3 non-collinear points. Okay, they're clearly not on the same line. I can't even try to get C on there, and so we're guaranteed these aren't collinear. But what I can do is I can draw a plane through them. I can go plane B, a plane through B, a plane through A, and a plane through C. And here we go. We have our whole new plane. Okay, and it slices this other one, as you can see on a line, and we can see that points A and B are guaranteed, parts A and B are still on this plane, right? Because A and B have to be on it. And we notice what happens with the line, right, that goes through it, is this line is also contained inside that plane, and that's actually a slightly different postulate. Okay, we'll get to that one in just a second. A line contains at least 2 points. Hopefully that's you can understand that that's true, but if we go back to our original 2-dimensional, for instance, is just because there's A and B on this, we know that it has to have at least A and B, right? But there's no limit, essentially, on how many points I can actually put on the same line. Oops, sorry, that was not actually on the line. But I can put an infinite set of points on this line. And what's even crazier, if I zoom in, right, I'll find that in between each of these points, right, there's a lot more little points. And if I keep zooming in, all right, a lot more little points. And I can just keep going and going because, again, these are infinitely small points. So every single bit, right, I can always find more points in between. And I can keep doing this over and over and over. Oops, that's not a... Right, and over and over. So I can find an infinite number of points, but right, the minimum amount that we have, right, is exactly 2. Right? So here we go back to our original. Right? We have points A and B. So through any 2 points, there's exactly 1 line. All right, and likewise, on any line contains at least 2 points, but realistically, it has infinitely many. Right? 2.4, a plane contains at least 3 non-collinear points. That's absolutely true. Okay. If we go back to, again, since we're dealing with a plane, right? Because I was able to draw this plane through here, if I even look at, understand that these were the minimum that I had in order to draw these. So a plane contains at least 3 points, but again, I mean, just look at the XY plane, right? So I have, let's just say that this is the X and this is the Y. I can put a point here and put a point here and put a point here, 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 here. I can put an infinite number of points, right? Likewise, in the coordinate plane, right? There's an infinite number of points. You can even just check looking at these grids, right? The more I zoom in, the more points there are. Okay, so and again, because this grid is kind of a representation of a plane, which is why we call it the XY plane. Okay. Next one, if 2 points lie in a plane, then the entire line containing those points also lies in the plane. Again, that should be evidence, and that's what I was trying to, oops, I don't know why that's doing that, sorry. That should be evidence as for when we go to our 3D model, right? I created a plane with A, B, and C, with A, B, and C, right? And we notice that that line AB that we drew originally was through that point. Now, again, if I try to move point, let's just go point C or point A. If I try to move point A, notice how not only does the plane move with it, right? Not only does the plane move with it, right? But the line is still in that plane. Okay, so if the line is attached to it, so every single point, right, that is on that line is now in that plane. Because if I were to go ahead and just put another point on this line, boom, boom, right, no matter where I try to put it, it's going to still be in the same plane. Okay, and again, if I try to move, let's just say A again, right, those points are still going to follow, and so every single point that's on that line will remain in that plane. Okay. Now we get to intersection. Okay, so if 2 lines intersect, and their intersection is exactly 1 point, and again, you've seen this a million times. If I go back to my regular, so let's just say I have this another point out here. Again, this is the definition of non-collinear because S, B, and any of these ones are not going to be collinear. So I can draw a line through S to any other point that is on here because there's exactly 1 line from S to F. There's exactly 1 line from S to B, from S to E, from S to A, so on and so forth. I don't know why that moved. So I can draw an infinite number of lines through point S touching this line, but the line that contains SE, for example, there's only 1. Okay. So now when 2 lines intersect, obviously they intersect at exactly 1 point. Because if I tried to zoom in here and I tried to find 2 points that this touches, right, that would never work. Right? It's always ever going to touch B, and you can't really tell, but I'm zooming in as far as I possibly can right now. Okay, so let me zoom back out, and that works also. Again, we've talked about this in, in Algebra 1 and even in geometry. Sorry, not geometry. In Algebra 1, right? Whenever 2 lines do intersect, it doesn't matter where they how they intersect or anything. Guaranteed that they intersect, right? It's only ever going to be 1 point. Now, I'm sorry, it shouldn't say that because if it does intersect at 1 point, right, or it could intersect at all points essentially, but then you'd have 3 lines that are collinear, so there's not really 2 lines anymore. It's just the same line. But right, anytime that they intersect, it's always going to be 1 point. Okay, and that works in 3D too. So if I draw another line and I go from let's just say here to K, okay, and no matter what, that's going to change, or that's not really going to change the idea that 2 lines ever only intersect at 1 point, or they intersect at all points, meaning they're the same line, or they can be parallel, in which they never intersect. Right? This again. And the last one, if 2 planes intersect, then their intersection is a line. Again, you need to be in 3D for this. And you can see, right, since A and C essentially are on, are where these guys are on in this same plane, we can see that if I connect the line between those two, A and C, right, you can see that the intersection is indeed a line. So whenever 2 planes intersect, right, whenever 2 planes intersect, we can have it be on a line. Okay, but it gets trickier when we have 3 planes intersect. So let me go ahead and clear this if I can. I don't know if it's going to let me clear it. Hang on. The 3D model does tend to freeze sometimes, so I do apologize. Here we go. Here we go. Let's keep going. Oh, nope. There we go. All the way back. We can keep those points there. So now if I try to draw 3 planes, so I'm actually going to keep it very, very very simple. So I'm actually going to do another plane that's along this other axis, so you can kind of see. Okay. So if I got B, C, there we go. I'm going to draw a plane for those 3 points. I'm going to do B, B, C. All right. So again, we have now the XY plane, and then we have the ZX plane. So if I have 2 intersect, right, they can intersect at a line, and they obviously intersect at this axis. So now I'm going to have 3 planes intersect, though, and we're going to kind of see what all 3 of their intersections looks like. So I'm going to use this point and this point. If I go through this one, B, and F, all right, we have 3 planes intersect. And although you're probably thinking, oh, that also intersects at a line, right? We have to think about, where do all 3 intersect? Well, these 2 intersect at this at the z, what we call the z-axis, x-axis. This plane and my xy plane intersect on the, let's say, x-axis, and then this plane and the xy axis all intersect on this one. So a bunch of different ways that planes are intersecting, but the question is where do all 3 of them do? Well, there's only one specific point, and that is right here. Okay, and that's along this, or it's right at the origin. So I look, the one point, the one place in common, right, that all of these points have is this point. That's the one point in heaven. So again, understanding that intersection, and I'm going to actually define that on your notes here. Okay, when you hear intersection, all right, we're going to give it a little bit of a new twist. Okay, the intersection of 2 objects is essentially, right, all of the common points between geometric figures. Sorry about that. That means any points that they have in common. So when we have 2 lines, they have 1 point. Right? When we have 2 planes, they have 1 line, which is an infinite set of points. Right? That's why it's an intersection. But now when we have 3 planes, oh shoot, where did my go? So now when I have 3 planes, right, they intersect at, the only common point is 1 exact point. Okay. And again, that can work any other time that we do this. It's not just, it is not just because of this one specific case. But now let's look at another situation where we have 3 planes intersect, right? We could also have, let's just go B here, and let's just do A, actually. Let's do that. Hang on. Let's go B, C, and A. We have yet a 3rd plane, sorry, a 4th plane. But if we just look at the light blue ones, right, those are 3 different planes, and their intersection is a line. So 3 planes can intersect at a point, or if they all look kind of like this, right, they can intersect at just a line. So it all kind of depends, and you just have to be able to visualize any one of these. Okay. So that's all I have today. As far as that's concerned, I will, in the next video, you will get to see a little bit about betweenness of points. Thank you.